What we're going to talk about is constitutive modeling. I don't know why that. So what's a constitutive model? We talk about a constitutive model. All right, it's some kind of proposed closure relation between two variables when we do mathematical modeling. Okay, and you know, for instance, Darcy's law is a constitutive model, right? It provides a relationship between pressure and velocity, fluid velocity, right? In terms of solid mechanics, I'm sure you know one, right? Hooke's law. And you probably learned it in the sense that it's some relationship between stress and strain, right? And you know, you might have seen it like this: stress is equal to E times strain. And this is true in one dimension, okay? But we haven't, in this class at least, even defined strain, right? And how many definitions of strain are there? When you think of strain, what do you think of? Change in length over length. Okay, so something like this. Strain is equal to, let's say, L final minus L O over LO, right? Change in length over length, okay? But I chose to normalize the change in length by LO. Why couldn't I change to, or why couldn't I decide to normalize it by the change in length over L final? Would that be a valid definition of strain? Why not? No, the change in length divided by the final length. So I have a bar, and I pull on it and deform it. And this is my change in length, and this is L final. This is L0. So why wouldn't that be a valid definition of strain? It is, actually. What if I decided to normalize it by, so I have the length, the instantaneous length during deformation, divided by the original length over the instantaneous length during deformation. Is that a valid definition of strain? It is. Turns out there's an infinite number of valid definitions of strain, whatever I choose to normalize it by, right? And so it turns out that the one we're most familiar with, this one, engineering strain, is actually what we call this. It's very important. It's probably not been emphasized to you in your other classes. But it's very important to label your strain or understand which strain you're talking about, because they can be, when you have a constitutive model that's linear elastic, so you have stress versus strain and the slope of it is E, right? Typically most materials are only linear elastic for a very, very small amount of strain. Like, you know, fraction of a %. But a lot of materials will deform considerably after that. They're not linear elastic anymore, including rocks, in fact, when they're under pressure. Will exhibit a lot of deformation past this linear elastic region. And it's really important. So for very, very small strains, all these definitions of strain are very, very close to one another. And it's not a big deal, okay? But when you have very large strains, it's really important. The difference in this definition and this definition in terms of stress could be quite a bit. Maybe something like that. Could be at a given strain value, the difference between engineering stress and this we call true or logarithmic stress can be maybe 60-70% in terms of stress at a given strain. So it's a big difference, and you need to be able to label your strain, understand which strain you're talking about. All right? So mathematically, when we talk about strain, so if I have a bar, all right, and I pull on it, so try to deform it. Okay. And let's say that any deformed position I'm going to call U. So this is the displacement, rather. The displacement in the x direction of any position along the deformed bar, I'm going to call U. If I were to give you a plot that will say U of x divided by, well, I'm sorry, not divided by, U of x as a function of x. And just for now, let's say that this, so I pull on this bar and I measure every single point along the bar. I measure U and I plot it as a function of x. And I get a straight line like that. And I give you the slope of that line, okay? And then I ask you I give you the slope of that line, and then I also say, give you some point U0 at x0. And I ask you, what is U1 at x1? So I give you U0, given U0 and x0. What is U1 at x1? That's a question I'm asking you. What is it? It's just an equation of a line, right? U1 is equal to the slope times x1 minus x0 plus U0. Right? Okay. So if x1 and x2, if x1 and x0 are an infinitely small distance apart, dx, right? So they're very, very close to one another. Infinitely close to one another, right? Then I have times dx plus u0. And I might also write u1 minus u0 is equal to m dx. Okay, now, what's the mathematical definition of the slope of a line? Well, what do we say like in a calculus term? or the derivative, right? The derivative of a curve, the derivative of the curve, right? So the slope at any point is the derivative, right? So that would be, in this case, du dx. Right? So we'll write du dx u1 minus uo. Okay, and then let's divide by dx so that we have it over here. Right? So then we have du dx u minus uo. Well, this is in fact what we call mathematically strain. Right? So it's the change in displacement over, and you know, technically this change in displacement is infinitely small because dx is infinitely small, right? So this is our 1D mathematical definition of strain. Right here.